Hello everyone, my name is Zhao. I'm from the Human Robot Interaction Lab at UMass Law. Today I'm going to present our paper towards mobile multitask manipulation in a confined and integrated environment with irregular objects. As you can see, I put a screenshot on the top to give you an overview of our work. So why do we do this work? The context here is robotic computations. Computations can bring state-of-the-art research into real-world scenarios. They have a long history of advancing both research and implementations. As you can see from those two photos, they're from the 2005 DARPA Grand Challenge, where teams need to program autonomous cars to drive through an off-road course. In our case, we entered the Fetchlt Mobile Manipulation Challenge last year in 2019. It's held at ICRA and organized by Fetchlt Robotics, and we won the second place. So the goal is for a Fetchlt robot to assemble gearbox kits as many as possible. To achieve the goal, the robot has to navigate in a narrow work cell, which is a 3x3 arena, pick up some complex mechanical parts, and put them into caddies. As you can see from the bottom left photo, they include large gear, screw, and a small gear. On the right side, there are gearbox and bottom. The narrow arena and the irregular objects make the problem very challenging. In terms of the implementation, we use Zhao for all of our components. Each component is a Caddy C++ library that allows other libraries to simply add a header file and call the relevant functions. For navigation, we use the Zhao's navigation stack, which includes the Monte Carlo localization, an A-star-based global planner, and a DWA local planner. For perception, we mainly use the point cloud library to process the data from the robot's RGBD head camera. For all of our perception tasks, we first run planar segmentation to get the points above the table, and then do Euclidean clustering. On the right side, we have a diagram for our architecture. Shown in the yellow block, we have the main component, which has 4 manipulation and 3 detection components above. The gray blocks are for navigation. We also extracted the common code to operate the Fetchlt robots and handle perception and manipulation tasks. For motion planning, we use the MoveIt library. After we detected an object, we'll generate a top-down grasp pose, and we add 2 waypoints above the object. From our experience, this can avoid unexpected behavior from using the rapid exploring random trace. Before any manipulation, the robot will scan the scene for collision avoidance. It will build an octomap from multiple scans in different angles. Having these angles is to account for the narrow field of view of the head RGBD camera. After the scan, to allow the robot to touch the object, it's going to manipulate, we crop the object out. We didn't use the built-in MoveIt feature, which requires us to match each single object. The first challenge we'll solve here is for the Caddy. Different from the common bin, the Caddy also has a curved handle and 3 different compartments. Initially, we converted the Caddy's CAD model to point cloud and tried 3 different methods to compare with what we get from the head camera. But none of them works in our case. We consider deep learning, but because the computation arena is unknown beforehand, we didn't use it because we're concerned that the transfer learning won't work well. We finally solved the Caddy detection by cropping the handle using a hatch heuristic and determining y-axis by PCA. To determine the compartment, we check the number of points of the divider area. The challenges here are the Caddy is practically symmetric, but with a divider only on one side, which can be easily occluded by the handle. Also, when a large gear is placed upright, it merges into the handle in the point cloud. We solved this by remembering the rotation that's recognized when the Caddy was empty. For the parts to put into the Caddy, we determine the type by the dimensions, the width, height, and the length. However, there are difficult cases. For example, the gearbox top and the bottom, as you can see on the right, are difficult to recognize when they are laying on their side. Sometimes stable segmentation may also remove some points from the parts. In this case, our algorithm will check neighboring cloud and consider it as part of the object. The screw case is special because the robot will need to pick them up from a bin, which needs a large number of times to find kinematic solutions. For the large gear, its head is higher than the shaft. The detection here is an example that we need to check neighboring clusters. For manipulation, because we need to insert the large gear straight into the chuck, the robot will have to grasp it very accurately, as you can see from the right photo. Before the robot grasps the large gear, the robot will need to know where the hole is for the insertion. To find the position, we look for horizontal and vertical planes. We first find the bottom plane of the machine, and then the vertical plane the chuck is attached to. Once the chuck is segmented, we found the pose of the hole by averaging the four corners of the rightmost plane. However, the hard part was manipulation. We had to overcome the reachability issue. Because for the robot to see the hole, it has to stop further away to the right. But to insert the large gear, it needs to stop closer. When the hole is visible, it's only 90 centimeters from the robot's shoulder, which is only slightly longer than the arm length when the robot has its wrist point downwards. For large gear insertion, the diameter of the hole is only 1 centimeter larger than the gear shaft. So if the robot grasps the large gear less accurately, the large gear won't get in. There is also no pressure sensor in the robot's head. So we use the joint effort values as its arm to let the robot retry after the large gear is inserted into the chuck itself, not the hole. There are also challenges when we implement the navigation. The ROS navigation stack didn't end up solving all the problems. The most challenging part is that the robot won't be able to get closer to the table because the underlying algorithm has to consider the sensor noise as you see from the right screenshot. To solve the problems, we write code to manually move the robot towards the table after it's roughly at its goal position. We also try to align with the table to have better rotation accuracy. After the computation, we kept improving our code base to make it more robust. Then we evaluate our system by having 29 stop runs. We measure the completion time and the task failure rate. The time is broken down into detection, planning, and manipulation. Most of them are done under 60 seconds, but the screw grasping is special because the motion planning has to avoid the bin. Here, the robot has a higher number of retries, and the retries on real robot takes time. We also recorded the failures. In total, the robot successfully assembled 13 full kits and 7 unrecoverable failures. In 2 of them, the chuck was not detected. The robot has backed up when being stuck. One time, the small gear is placed outside of the caddy because of the point cloud noise. Another time, the large gear is not grasped perfectly, so the insertion failed. In the remaining 2 times, the large gear collided with the back of the chuck. To solve the navigation issue, the robot can drive to the center of the arena and retry. In fact, the robot recovers most of the time, such as minor collisions due to the RGBD camera noise. To conclude, we summarize 3 challenges remaining for the robotics community. There are autonomous near-object navigation, such as table. This is important for tabletop manipulation. We also need to improve the detection for complex and concave objects, such as Caddy and the large gear. To achieve this, we need to benchmark and develop algorithm designed specifically for manipulation. We also need the robot to manipulate in confined space, such as inside the machine for large gear insertion. The obstacle avoidance becomes more interesting when the space is narrow. Thanks for your attention. We also put our code on GitHub, and hopefully it can help you if you have similar issues. If you have any questions, feel free to contact me. Here is my email and my personal webpage. I also put our lab website here where you can find more work about our lab. And again, here are all the people who contributed to the project. Thank you for listening.